Yeah, most.
Does he speak?
Yeah, no, he's just gonna write the whole time, I think.
I'm gonna speak. Okay, so we have a bunch of people that I'm not going to write the names of because they're so late starting out. But we have my collaborators are excellent, so I'm not writing their names, but it doesn't mean anything about that. Okay, so thanks a lot for having me here, and thanks a lot for joining. So today I'm gonna talk about how we can probe small scale structure using gravitational waves. So this is based on this paper I wrote with Reza Ibadi, who is a student at Maryland, with Amara McHugh, who is a visiting student at Berkeley, Han Zai, who recently started his PhD at Chicago, and Yanta Wang. So this is something we put out last summer, like the previous summer, and then there's also something we are thinking about now to improve some of the computations. So please ask questions. I hope to give you at least some flavor of what this idea is about, and feel free to stop me whenever you have any questions. So first, let me start with talking about what I really mean by small scale structure, and for that I need to go back a bit more, and I first will talk a bit about how these structures were generated, starting with the early universe. So the point is, when you look at the CMB, and when you look at also the large scale structure, like in the distribution of galaxies, we see very interesting patterns on them. We see anisotropies on the CMB, we see homogenities in the distribution of galaxies. So one question you can ask is, where are these structures coming from? Why is CMB anisotropic, for example? And in some sense, our best guess is that when the universe was very young, it went through a period of cosmic inflation. And basically what happened is that during this inflationary epoch, the universe expanded very, very rapidly for like the horizon. Like for example, if you take any 2 points, the distance between them, it increased exponentially fast. And as a result, very, very small scale quantum mechanical fluctuations, they got stretched to very, very large sizes. For example, if you were to draw, for example, let's say this is the size of the causal horizon during inflation at some instant, then what was happening during inflation is that if you take a small subhorizon quantum mechanical fluctuations, then as the universe expanded, this fluctuation, it got very rapidly stretched to some super horizon size. Okay, so it became very large very quickly. And as you expect, just from causality, when things are separated by a distance that is much bigger than the horizon, so importantly, the horizon size remained the same. So because this remained the same, because this size is much bigger than the horizon size, this mode basically got frozen in time, so it stopped evolving. Okay, so the function of time, the amplitude, for example, became constant. And eventually, these modes, they like after inflation ends, after you get into the radiation or matter-dominated era, the horizon size changes in a way such that these modes, they become smaller in size compared to the horizon size, and that's when they can again seed density perturbations that we see in the CMB and large scale structure. Now, one, of course, as this is something that you probably know very well, if you start with this type of a setup, then if you consider, let's say, 2 points, if you take those 2 points inside the horizon, because they were inside the horizon, they could have talked to each other. But then as inflation was happening, these 2 points, they got separated by a distance that is much larger than the horizon. But then the pure fact that they were inside the horizon at some very early time, it basically means that these fluctuations that we eventually see in the CMB and the large scale structure, we expect correlations between them. So for example, if you compute the 2-point correlation functions of these density fluctuations, you expect to get a non-zero answer. And that is one of the primary probes we have of primordial physics. And what I will denote by, so I'll basically use the symbol zeta to denote the density fluctuations at some given point x. And because of the fact that everything was inside the horizon at some very early time, you expect some non-trivial correlation between density perturbations at 2 different points. So you expect this quantity to be non-zero. Now, it is also a very interesting aspect about inflation, especially for the simplest low-roll models of inflations that we have, is that it predicts that this correlation function in position space is scale invariant. Okay? It means that it does not depend strongly on the separation between these 2 points, x and y. What that means is that if you Fourier transform this object, so K1 and K2, they're just Fourier modes corresponding to these 2 positions, you expect this quantity to go as 1 over K1 cubed, and then there's some delta functions that just characterizes the fact that you have translation invariance. So this is just what you get from simplest models of inflation. So just for the convenience of notation, what we often use is to define a quantity I'll call delta zeta squared. So it's basically the power spectrum with a normalization. So we define it as k cubed zeta k zeta k. There are some factors of like 2 and pi, not super important for this stuff. So what I have done is something very simple. I've just taken this factor of k cube over there. And because of this assumption of scale invariance, what we expect is that this function, it should not have a very strong dependence on k. Okay? So it can, for example,
Rid of the delta.
Huh?
You got
I got rid of the delta. So what is
the
this?
easiest way to do it is to Fourier transform in one variable and keep the other in x.
Yeah.
Or y.
Yeah, absolutely. Yeah. So I'll sometimes put this prime factors on the correlation, and the primes basically mean that I've taken out this delta. Okay, so
are you using? This is really good. Are you using zeta here to reduce the number of deltas on the board? Zeta is not the usual symbol here.
So people use
Because I was complaining when Roman used delta 3 different ways in his last talk.
there is a body of literature which uses this gauge invariant density perturbations on like.
So your zeta is supposed to imply that you're doing something that's more coordinate free.
Yeah.
Good, fine.
Yeah. So I'll relate zeta in a moment with, for example, fluctuations of the inflaton.
I see. Okay.
But there is a gauge invariant way of defining this, so that
I'm surprised.
all right. So this is what you expect based on simple models of inflation. So now, what do we know from data? Well, famously, we know how much anisotropies there are on the CMB roughly. We of course measured the 2-point function very well. And if you translate that back to a requirement or a restriction on this power spectrum, the dimensionless power spectrum, this is basically what you know. So you expect that on scales which are pretty large, so of course this axis is not to scale, as is obvious, but on this very large length scales or small values of momenta, which I'm plotting here, Planck and also large scale structure, they have told us that the value of delta zeta squared is roughly 2 times 10⁻⁹, And we also notice that there is a small tilt in the spectrum, a small red tilt. By red, I mean disorientation. By red means basically the power is decreasing as you go to higher and higher K. And this tilt is roughly 0.04. Okay? So this is what we know. And we know this value like up to values of K, which are like roughly 1 inverse mega per second. Okay? Now the interesting aspect is that, as is clear from this plot, in typical models of inflation, you do not just stop at producing these many K modes. There are orders of magnitude many more K modes. In fact, you can show like if you have like a standard inflationary scenario with maybe Hubble scale of 10 to the 13 GeV and high reheat temperature like gut scale reheat temperature, you can produce K modes which are as big as 10 to the 20 inverse mega per second. But then what we are seeing here is that the main constraint, like the dominant constraint we have is just on this part of the parameter space. If you try to ask what happens at larger values of K, you do have some constraints, but then they are of course much weaker than what we know from Planck and large scale structure. For example, there are bounds coming from CMB spectral distortion, but that typically says that for K roughly between 10 and 10 to the 4, this should not be much larger than 10 to the minus 4 or so. So this part we have constraints from spectral distortion. There is an even weaker but kind of very broad constraints that comes from the requirement that if the perturbations are too large, you will basically primordial black holes would form. And of course, they are bad in the sense that if they form too early and if they're too long-lived, then they would give rise to matter domination very, very early on, and that is inconsistent with what we see from data. But that restriction is mostly saying that delta zeta square, or the power spectrum, it should not be larger than 10 to the minus 2. So this is basically what we know using data at the moment. Yeah. But then there are all these modes, right, in this very big part of the parameter space where we do not have any strong constraints, such as like constraints as strong as coming from Planck or Lyman. So this is basically going to be the idea of this talk. We want to understand in what ways we can probe this parameter space, what kind of physics can give rise to non-trivial, or what kind of inflationary physics can give rise to non-trivial signatures here, and also in what ways we can probe this parameter space.
Let's ask the question about the primordial black hole. That must be a function of K somehow.
Sorry, could you
So
repeat?
the primordial black hole bound is presumably a function of K. So what's it really look like?
It is not a very strong function of K. So roughly speaking, it's always like 10 to the minus 2, and the
Over which ratio of K does it mean?
So I forget the exact number here, but it's roughly, it persists at least as much as 10 to the 18 inverse mega per sec. If you go to very, very large Ks, eventually the black holes would evaporate and they won't be constraints.
So you're saying anything less than 10 to the 18?
Yeah. Yeah. And the reason why this is not strongly sensitive is that you are basically asking that if your power spectrum is at this level, what is the chance that you are basically sitting on a tail of some Gaussian distribution. So you have to go towards the peak of the distribution from the tail. So that's why here you have to there is an exponential penalty.
I just
here.
thought it would depend on how much time it would have to redshift after formation. So that would introduce in K.
Yeah, so there is some dependence
it's
here,
not-
but it's not.
yeah,
it's
yeah,
not super.
yeah.
It's exponential versus algebraic.
Right.
Because you are exponentially sensitive
Right.
to the fluctuation to form a black hole.
Yeah.
And all the algebraically sensitive to the epoch for energy density.
So there should be a lot of Okay.
Yeah, so you basically, the probability is basically like an exponential, but this is some over density. So you have to be, you're basically fighting against this number, which is very small.
And if the Planck large scale structure limit if that is created by a vanilla, like the sort of simplest inflation models, then you do expect that line to go all the way across, right?
Yeah.
With maybe very low tilt, or maybe it flattens out or something.
Yeah, so it's really not yeah. So if you expect your vanilla model is valid, then yeah, you do expect this to go like this. But so there is one important target here, which I have important like proposal here, which I have not written about. So there is a proposal of super pixie. So that basically aims to if you have this
proposal of what?
it's a future version of Pixie, which may not happen. It's called Super Pixie. The point is if you extrapolate this line, at some point you have also some power in for these values of k, and you just by standard model, like just by standard inflationary paradigm, you would expect some irreducible amount of spectral distortion. So Super Pixie proposed to like get to that target. So I'm just referring to that in reference to your question.
Good. And the one last bit of my question, I have an intuition that there's some theory lower limit. Like I can see how it's very easy to add power theoretically, but is there some floor on the power, or could could that power fall away and you really have no power out here?
I'm not sure.
Inflation model, anyway.
Yeah, I'm not sure if there is something you can say in a model independent fashion, but of course, like one important aspect is that if this is your picture for an inflaton potential, like the idea is that if the field is rolling over here, it's fluctuating and you're generating these modes, but eventually as you are rolling towards the minimum, because you have to reheat eventually, right? So as you are moving over here, you generically would expect some large perturbations. So it is true that maybe by playing with some potential or other cosmology, you can create a dip or you can bend it in this direction, but eventually it's going to come up because over here the density fluctuations are expected to be large.
I'm confused. I think what you're doing, but correct me if I'm not picking up, is you're trying to translate into today's scales essentially what's going on at very, very high redshift.
That's right. Yeah.
Because of course we know that regular structure form nonlinear stuff modifies it.
Yeah.
But you could have tried to show it to us at very high redshift, but somehow you find it helpful to think of it in today's scales. Is that the
yeah, that's right. Because the main observable I'm going to focus on is gravitational waves, and we'll see that like there's a direct one-to-one relation between the k I'm drawing here with the frequency of the gravitational wave.
But just to clarify, this is not what you expect in structure in our universe today.
Yeah, so
in regular mass density, for example.
Yeah, so right, so yeah, so those good. So if you have some, so that's also that also can give you some sensitivity. So if you are, so there is of course some relation between a k mode and the mass included in that k mode. So you could relate, like given a value of k, you could relate like the halo mass included in the structure. So
this is like the primordial.
This is the primordial
density perturbation before the transfer function and the
Yeah.
linear growth.
And it's just for some other reason that it's, well, because he's going to be talking about gravitational waves, he translates it into days.
Days
scale.
distance.
Yeah,
density,
yeah.
yeah.
In a length scale, but not the
And
amplitude
how
scale.
does the
Yeah.
the length of inflation affect your answer?
Sorry.
How does how long inflation ends affect your answer?
Yeah, so yeah, good. So that basically tells you to what like how far.
That's what I thought. So that's really the answer to David's question, is that it depends on how long inflation lasts.
Yeah, so
Understood.
right, so you
So that's why it's critical to measure, because in principle, it's going to directly translate into an inflation parameter.
that's right. Yeah. So what you do is that you basically take the ratio of the scales and take a log, so that will give you the number of unfoldings.
Understood.
All right, so good. So of course, yeah, as we are discussing, if we really don't know what happens out here, and given that, you can ask just like two broad sets of questions. One aspect is that from the perspective of mechanisms, we can ask, are there reasonable mechanisms that can, for example, enhance structure at small scales? The reason I'm focusing on enhancement is that it can give rise to interesting signatures that we can probe using various experiments. And also, like, if there is really like this sort of downturn, if you want, then questions like exactly what happens during the end of inflation and so on, those might also become relevant, because of course, like eventually we want to know the full shape. But in cases where you have some sort of enhancement, you can still answer questions without really talking about how inflation ended, because you're probing scales which exited when the inflaton was not near here yet, but still on kind of the flattish part of the potential. Okay, so now of course this question has been asked before, and there are, like, from the perspective of mechanisms, there are several proposals. One of them, it goes by the name of ultra slow roll inflation. I'm not going to talk about this today, but I'm just wanted to give you a very basic picture of it. So there are different models for this, but one critical aspect of various models is that you basically need some sort of a potential which is very, very flat over a range in field space. So this is V of phi as a function of phi. So what can happen is that as the inflaton is rolling down over here, you generate the fluctuations that we see on the CMB and large scale structure. But then there is a later part where the potential is extremely flat. And if the potential is extremely flat, there is a way in which you can have large density perturbations. And one simple way to see that is that if you try to write out density perturbations in terms of the velocity of the inflaton field, so I'm not going to go into the derivation of this quantity, but this is basically what you get. So what you want to write is you want to ask, like, how large these fluctuations are, and you want to relate that to the scale of inflation and to the speed with which the field is rolling. And this is basically what you get. I'm happy to go into the more derivation of it, but just for lack of time, let's just take this value for granted and see what this part of the potential would do. Good. So the point of these sort of models is that you generate the CMB and large scale structure fluctuations from this epoch, but when this field comes over here, because this part of the potential is so flat, this field slows down significantly compared to that part. In other words, phi dot becomes much, much smaller than the value of phi dot that you had when CMB fluctuations were generated. And as a result, because this guy gets smaller, you can enhance the perturbation.
Is there any rationale for this except that you want to enhance them?
So that's literally my next comment. So this is not why. So yeah, precisely because of this reason, there are issues, or if you want, like, it's somewhat of a philosophical question as well. Like, we typically don't expect to find such flat plateaus on the inflationary potential, because radiative corrections or corrections from other fields, you would typically expect the mass of the inflaton to be lifted, not get extremely small. So that's why, like, although you can model build and you can play with shapes of V phi, there is a question of, like, how natural these kind of shapes are.
And also it makes coincidental the red tilt. Right?
Exactly.
Because in the standard picture, red tilt
Yeah.
is a sign that inflation is about to end.
Right.
Because actually many people argue that it's a prediction.
Right.
Sorry, could you say that again, Sergey?
Well, it makes coincidental the observed red tilt, right? Because kind of in the simplest model of inflation, one expects to have red tilt because it's a sign that your phi dot grows, so approaching the end of inflation. And here it becomes completely.
But it shows that in these very simple scenarios, and a direct observation here can be translated into a potential, right?
That's
Like,
true.
in these trivial models, you
yeah.
can take whatever you see there and just turn it into a potential.
Yeah. So good. So yeah. So ideally, if we had something as powerful as Planck spanning over many K modes, you would do that greatly. I'll talk about gravitational waves. So they're very powerful in the sense that they operate in a very complementary region where we don't have other probes, but still we're not going to be, I mean, just to spoil the story, we're not going to be able to reach something as powerful as this. Yeah. But yeah, if we were to, then yeah, absolutely, you're right. Yeah. Okay, so good. So that's basically what I wanted to talk about. This sort of models. There are also other models where you put, like, spikes on the potential and you can enhance data in that way, but I'm also not going to talk about that. Okay, so So what we are going to discuss is that we're going to have one extra ingredient beyond the inflaton. We're going to imagine that there is a curvaton-like field, which I'm going to call sigma. It's a light field in the sense that its mass is of the order or somewhat smaller than the inflationary Hubble scale. And I will show that if you have such a scenario where you have another scalar field during inflation with this type of mass, and if this survives after inflation for some time, so it's somewhat long-lived, then without like playing these games with the inflaton potential, you can have scenarios where the density perturbations can naturally get enhanced at small scales, at large values of k, and then we'll discuss like what sort of signatures they would give rise to. Okay, so this would be our main ingredient. So we want another extra scalar field with this type of mass, and we want this guy to be somewhat long-lived after inflation. So it should not like decay right after inflation. It should be a
So
bit
who
longer.
decays first, the inflaton or the?
Sorry?
So the inflaton decays before this graviton?
It could, yeah. So inflaton could decay before sigma. So then you have a basically like the cosmology would be dependent on how much energy density you have in sigma versus how much in standard model radiation. Yeah, but yeah, you're right. So yeah. So I mean, yeah. So we'll yeah. I don't have anything extra.
So what are you assuming? Or you're not assuming either way? Or you're assuming...
We will good. So in this paper that we put out, we will assume. So this will be important later on. We'll assume that at the time of sigma decay, rho sigma, like the energy density in sigma, it's smaller than the energy density in standard model. You can relax this assumption and also consider cases where sigma is even longer lived, so that it actually dominates the expansion history for a bit. That case is also interesting. Some of the technical aspects for the computation of gravitational waves, those are a bit different. But for this talk, I'll just focus on this.
And you really mean rho standard model there, not rho inflation, not rho inflaton.
I really mean rho standard model. So I'll assume that good. So I'll assume that inflaton decays first into the bath, and there is also the sigma, which dilutes like matter. But then when sigma decays, this is somewhat smaller than standard model radiation. Yeah.
Sorry. As far as the curvaton field goes, are there additional motivations, like when we might expect this to exist, or are you just kind of saying it should be there so we can see this like small scale?
Yeah, so good. So yeah, so first of all, these sort of light scalars, they very easily arise in UV motivated scenarios. But the question you can ask is, why would you have this sort of relation? And there is a very simple way that this can arise. For example, just imagine that you have the Ricci scalar and a sigma square coupling in your potential with some constant C. So this is like a simple operator you can write. It's a dimension 4. So for order 1 values of this coefficient C, because this Ricci scalar is of the order of Hubble square during inflation, you very easily get like order Hubble square.
So you know the problem with that, of course, is that you can write down a zillion other operators too that are bigger than this.
Yeah. So yeah, so this will be we'll see like why, in what ways this will be relevant as well. But the qualitative idea is that if the masses are much bigger than Hubble, then they don't survive as long. You don't produce them as well. So all right, so good. So let's try to understand like what happens if, like what is the cosmology of these fields. Okay, so if you just write down the equation of motion for the sigma field, so dots mean time derivatives. This is what you get, okay? So this is just the standard Klein-Gordon equation. This is the gradient term, this is the mass term, this is the Hubble friction. So now one thing you can immediately say is that let's first study the solution where the sigma field has a homogeneous mode. Okay, so it's not spatially varying. So k is equal to 0. And then you can drop this term. Let's also consider that limit where the mass is somewhat smaller than Hubble. In that limit, the field, it slow rolls, and you can show that up to like order m square over Hubble square corrections. You can also drop this guy. So now you have a very simple equation. You can solve it, and what you basically see is that the solution is basically m squared t over h. There are some factors of order 1 factors. Next.
I'm sorry to give you a hard time, but you said rho sigma is less than rho standard model, but H is much less than rho standard model, right? So why would M be much less than H?
So this is happening still during inflation.
This is during.
Yeah. Okay. So that's important. So thanks. All right. So okay. So this is what you would expect. Now the point is, one thing that you do not know about inflation is that how much inflation there were before the modes that we observe on the CMB were generated and exited the horizon. Okay, so we do not know what was happening, for example, at this part of the plot, simply because those modes, they have not entered into our horizon yet, so they are still super horizon, and we have no idea of like what their properties are and so on. So we do not know like how many. So what we kind of know is how much e-folding could there be after the CMB modes exited the horizon, but not before that. But then, of course, these fields, they were undergoing this dynamics the entire time. So what will typically happen is that because the mass is somewhat smaller than Hubble, but not extremely small, this exponential decrease will eventually kick in if you evolve the system for a very long time. And for example, if you assume that there were like order 100 e-foldings before the CMB modes exited the horizon, and if you say that m squared is 0.2 Hubble squared, just to take a benchmark, then this sort of exponential suppression, it becomes of the order of 10 to the minus 3. Okay? So this is just to show that even though the field is not seemingly doing much over a long time, it does, like its amplitude does decrease quite a lot.
You're assuming the minimum during inflation is the same as the minimum after inflation,
That's right.
which is not.
That's true, but yeah, the entire time I'll basically focus on some n square sigma square.
But there could be Hubble corrections during inflation.
That's true. There could be, but yeah, I won't be talking about that. Yeah. Okay, so what that means is that if you just focus on this potential, maybe at some point the field was sufficiently shifted from its minimum. So let me just call this minimum to be sigma equals 0. But then as these pre-CMB inflation, as these epochs were as the universe was going through these epochs, this field will gradually start coming down towards the minimum because the amplitude is getting exponentially diluted. So eventually, what's going to happen is that when you are in this part of the plot, you might be having effects where you have a field that is localized at the bottom of the potential, but then, of course, it's quantum mechanically fluctuating up and down. Okay? So it's not, of course, exactly strictly localized to sigma equals 0. There are going to be these quantum mechanical fluctuations, and we'll see that these quantum mechanical or stochastic fluctuations, they are going to create this blue tilt effect that I was talking about. By blue tilt, I mean a spectrum that increases with k. So just to summarize so far, if you have like order Hubble masses, you expect this exponential suppression, you expect the localization of the field towards the bottom of the potential, but even then there are going to be these stochastic quantum mechanical fluctuations, which are going to give non-trivial effects.
And so basically, coming back to Lisa's question. So essentially, assuming these terms are sigma squared, which you wrote before, they're negligible, right? Because they wouldn't lead to this.
You mean this? Or?
No, sigma squared R, right? The one on the top, right?
Yeah. Mm-hmm.
Because in that case, the minimum will be a different place.
I mean, you still have to the extent you still have like R to be approximately constant, you still have a Hubble square mass.
Yeah, it's a Hubble squared mass, but the minimum of the potential
Would be different after inflation. That's true.
Right.
So yeah, so probably a fair way to say this is that you have, yeah, I mean if you also have this contribution, you probably need also some Bayer contribution to the mass so that guy still survives after inflation.
Yeah, but the point is that you have a different minimum after inflation, essentially, because you would also have higher order terms.
So it looks like generically one doesn't expect actually this exponential suppression, right? Because you expect the minimal after inflation to be displaced.
Yeah, so right, so that could for sure happen if you play with these two terms. So in this talk, although I'm going to assume that you have the same minimum like during and after inflation. I think that case is also pretty interesting. All right. So okay, so let me talk about what happens in detail about like with this what happens with these quantum mechanical fluctuations with some simple cartoon setup. So one thing you can imagine is that let's just go back to the expression we had for this field, but now let us restore the momentum modes. So we have so now I'm focusing on a given K mode. Okay, so it's a Fourier mode, but then I still want to focus on the case where m squared is somewhat smaller than Hubble square. So in that case, what will still happen is that at the level of this Fourier mode, you can still obtain a Sorel type situation where this term is small, like you can drop it compared to the other terms, and then you can still write a solution that is like a super horizon expression. So so you can write a solution when k is much smaller than AH, where A is the scale factor. This is the Hubble scale during inflation. This is basically the statement that the size of the mode is much bigger than the horizon. So if you focus on this type of K modes, then you can still write just over there, just like what we have on the other part of the board. You can write sigma k as exponential of minus m squared t minus t star over 3h. So this is exactly the same solution as that. We have one additional quantity, which is t star. So that basically tells you when this mode exited the horizon. Okay? So what's going to happen is that when the mode was inside the horizon, you have this term, which is important. You have fluctuations going on. But again, eventually this mode gets larger in size compared to the horizon. So this term drops in significance. This term also drops in significance. But all of that happens only when the mode has exited the horizon. So that's basically this time t star. Okay? So let's now, like, keeping that solution in mind, let's just draw one diagram which will make it clear why we expect blue tilt. And this diagram you have probably seen before. So this is I'm just plotting the size of the co-moving horizon as a function of time. So once again, A is the scale factor, H is the Hubble scale. Now during inflation, at least the parts that we can see, H, let's say, roughly stays a constant, but of course the scale factor is increasing exponentially. So on a log plot, you have the horizon, which is decreasing. The horizon size is decreasing with time. So this is during inflation. And then once inflation gets over, this quantity increases as a function of time. So this is, for example, what you would have, for example, during radiation evolution. Okay. All right, so now keeping that solution in mind, let us consider two different K modes. Okay, so let's consider. So this is, I should clarify, this is a length scale. So let's consider two different K modes, K1 and K2, but because there's a length scale, there's a K1 inverse, K2 inverse. Okay. So what's going to happen is that this mode, like whenever, so this is AH inverse, that is basically this line over here. So whenever this mode crosses this point, that's when the mode exits the horizon. It basically, again, mostly freezes up to that exponential suppression. Okay, so, and then eventually it comes back inside the horizon when K becomes larger than AH, and then it does other things that I'll be talking about. But then what is happening with this other K mode is that it also exits the horizon, but at a much later time, because it's a smaller length scale mode, so it exits much later. So it exits over here, and then again it comes back inside and does other things. So here's the key point. If you consider these two K modes, then you see that for this mode, it spends a much longer time outside the horizon compared to this mode. And as a result, because of that exponential suppression, you would expect the power in this K mode to be much smaller than the power in this K mode. Because this mode, it just has undergone lesser amount of dilution compared to the other K mode. Okay? Now, what that means is that here, of course, like we have K1 inverse bigger than K2 inverse, and that basically means that K1 is smaller than K2. That means if you go to larger K modes, there is lesser dilution and there is more power in those K modes compared to smaller K modes.
Don't you have to fine tune M to H?
Yeah, we don't have to, like, there is some window for sure. So if M is too small compared to H, you expect like a flattish spectrum.
And if it's too large, you expect nothing.
You expect nothing, that's true. So it is true that you have to have some window around Hubble. That's true. Yeah.
Will you tell us how we look for those? Who cares how you make them? How do we look for them?
Yeah, I'll talk about it. I still have some time. Yeah. But let me just wrap up on this aspect. So
I don't want to harp on this, but the fact that M is of order H is completely coincidental unless your potential is driven by.
Maybe we can chat more about it, but I think it might also be just a matter of science, right? Because if you don't have like tachyonic signs, for example, like if you have like to the extent like R is plus Hubble square, if you have a setup like that, I think you don't change the location of the potential minimum.
Well, because you wrote it down that way, I mean, you would generically have M squared sigma minus sigma prime squared, right? You assume that they had the same minimum.
Can you guys explain it to the rest of us? This you keep talking, you and Sergey, you keep talking about
I'm
this
just saying
R.
that in general.
What is this R?
Curvature.
Why do we care? Yeah, I understand R is curvature. Why do we care about this coupling?
Well, that's the argument why it's natural to have masses for the H, right? Because that coupling is not protected by any symmetry. Generically, you expect it to be there, and then it gives mass for the H squared
During inflation.
during inflation.
But it's always a massive order H squared, but H changes after inflation. So if that's the only source of mass, your mass would change a lot, and unless your minimum is guaranteed to be at sigma equals 0 before and after
So you
inflation.
cannot just postulate M over the H. You need to generate.
I mean,
it.
you can, but then it's just as unnatural as assuming this flat section in the potential.
Oh, it's
Well,
the
it's
nature of the
coincidental.
signal.
You could imagine the phi is a pseudo-Goldstone, so the coupling to R is suppressed by parameter epsilon. The same epsilon appears in the potential. The potential, you have less suppression, so it's dominated by the potential. Then you assume that actual times the scale is of order of H squared during inflation.
But
That's
where it matters for
But
you
it's
the
coincidental.
potential, that minimum, because K, the sigma K mode with non-zero K will not be affected by that, right? So where it matters for you that the minimum of the potential.
Well, I guess you yeah, so that's I think so. Good. So what happens for the rest of the cosmology, like after inflation? So there are some assumptions there. So what I'll assume is that because of this quantum mechanical fluctuations, you have some sort of RMS displacement of the field, and then you have to ask like what is that field doing after inflation? And for that, I'll just assume that it will roll down to the same minimum. But it might be possible to like relax that assumption. We have not looked into that very carefully.
So, sorry to ask you another question about the R sigma squared term. But so there's sort of a standard way of counting powers of M Planck when you have higher derivative terms involving the Ricci tensor or Riemann tensor, right? And I mean, basically, you expect R to come with 1 over G Newton everywhere.
With a G Newton, not one of them.
Well, I mean, in
Phi
the
square R, there's no G.
I mean, in the I mean, if I'm
okay,
thinking
go
of this
ahead.
as like a correction to the Einstein-Hilbert term, right? If I give sigma a vev, right? So I would have R over 16 pi G Newton. So that's like M Planck squared R sigma squared divided by MUV squared, where MUV is some new mass scale.
Sorry, you're saying M Planck squared. Sorry, you're saying R.
Yeah.
There's not a mask.
This is a dimension 4 operator though. So
No, well, I'm just saying, shouldn't I expect the R sigma squared term to be actually enhanced by a factor of M Planck over MUV squared, where MUV is some scale?
I'm not sure if that is always true. Like it could be model dependent, right? Because here I'm just saying you can have a scenario where it's like M Planck squared R plus some CR sigma squared.
Yeah. I guess I just expect C to be of order M Planck squared over MUV squared, but we can talk after.
I think he's just saying that it's natural to have a term like rho over MUV squared.
Yeah,
not just rho over M
So
Planck
the
squared.
R
Why is
counts
the
like
other
to the
one?
derivative. Look,
Yeah,
that
if there's
R phi squared counts like a kinetic term of sigma. It's to the derivative.
So I'm going to allow Soubhik to
All right, but
continue.
I'm very happy to discuss more about this, but let me just get to the final aspect. Okay, so if you just compute this effect by putting together numbers, you'll see like the tilt you get is m squared over Hubble squared with some order on factors. So what that means is that if you were to plot the dimensionless perturbation in sigma as a function of k, instead of like that falling behavior over there, you would expect to see something growing up with a tilt which is given by this method. So of course, like there is some sensitivity. Like if m is literally 0, you expect this.
That's
to be
like
flat.
the difference in the power law index. That's what you mean by tilt.
That's right.
Okay.
Yeah, that's right. Okay, so I have like 10 minutes. So let me spend like maybe 5 minutes regarding the cosmology a bit, and then the last 5 minutes regarding gravitational waves. So of course this is just the power spectrum in sigma, but what we are interested in is the power spectrum in the density perturbation. So we have to tie back to that story. So here's the aspect about the post-inflationary evolution that we have. So what I'll imagine is that you have this inflaton field during inflation as standard, and then there's of course the sigma field, and if you just plot the energy density as a function of time, I'll assume that phi, it decays into radiation, so it dilutes as like a to the minus 4. Sigma, on the other hand, it is subdominant during inflation, but then it dilutes only as like a to the minus 3. And then at some point, it decays back into radiation. So you have again like a to the minus 4 dilution. So with this in mind, if you just write down what is the delta rho over rho, then you can do it in a very simple way. You can say you have two parts, radiation and sigma, radiation coming from the inflaton, and then here's the total thing. And then if you just do the algebra, you'll see like there are two pieces, which is delta rho r over r, 1 minus f sigma times plus delta rho sigma over rho sigma, f sigma, where f sigma is the energy density in sigma over the radiation at the time of the sigma decay. Okay? So he's just saying you have two components in your system, fluctuations in either of them would source some density perturbation. So of course there is some gauge invariant way of writing this, but the point is if you just take the square of this because the power spectrum is basically delta rho over rho squared, you will see that there are two pieces. So let me write the square of this as zeta squared. You'll see that there are two contributions to it. One is delta rho over r square with this factor, 1 minus f sigma square. And then there is a second piece, as you expect. So delta rho sigma over rho sigma square. Because these are two different fields, you don't expect any cross terms. So what that means is that if you now add these two contributions together, what you have is on very, very large scales, you can have a scenario where this term, it basically dominates the total density perturbation. So you have a standard red tilted spectrum. But then if you focus on larger K modes, those K modes, they enter the horizon when f sigma is appreciable, and that's why this term takes over. And then you can have, so you basically have this contribution from phi, you have this contribution from sigma. So if you put them together, you can have a situation which is like this. So this is
the x-axis is,
sorry, the x-axis is same as that, so it's still k.
Oh, it's k.
Yeah.
Okay.
So the idea is that these scales, these values, they are well constrained by Planck and large scale structure. But then you have this growth at large k, which is very gradual. The precise value, of course, depends on the mass. But then you still have this growth, and eventually, at some point, this gets cut off, which depends on the cosmology of it, like exactly what value of f sigma, for what value of f sigma decays and so on. So eventually, like there's a turnover, but I'm happy to go into if you're interested. Okay, so this is basically a situation then where if you have Hubble mass particles, you can have a blue tilted spectrum at small enough scales, and we'll see like how that can source gravitational waves. So that's basically the last part of it. So okay, so the idea behind sourcing of gravitational waves from these large density perturbations is very simple. You can just start with writing down, for example, the perturbed Einstein equations. I'm assuming that just for simplicity, you're in some flat space. So some T mu. I'm not writing out order 1 factors. This is basically standard expression for gravitational waves. It says like it's sourced by the energy momentum, let's say. Now the point is T mu, if you have a scalar field, it's quadratic in the scalar field. So it would schematically have a contribution which is roughly like this. Okay? That means if you were to study, so here we are interested in the fluctuations of the scalar field. So that means T mu, the source, you can basically like replace this field phi with the perturbations, so zeta. So that basically means that these perturbations, which are spin 0, at the quadratic order or at that second order, they do contribute to a non-zero energy momentum. But at the linear order, there is nothing, just because the spins don't match. So what it means is that if you have some enhancement in zeta, the contribution to the T mu nu and hence to H mu nu would be larger than what you expect. And if you just go through the algebra, what you'll see is that if you finally compute the energy density in gravitational wave today, then you'll have the standard 10 to the minus 5 that you get also for example, radiation. But there is this extra contribution coming from this effect. So T mu nu is quadratic in zeta, but the energy density itself is a quadratic of h. So h square is basically sensitive to 4 powers of zeta. That's why you have power spectrum square. And what is important is that the precise values of the momentum modes here, they would directly determine the frequency of the gravitational waves, right? Because you basically have a diagram where you have one factor of h getting sourced by like 2 fluctuations zeta. So typically you would expect these momenta to be comparable to each other. And that means the frequency of the gravitational waves that you see, they're directly connected to the values of the k modes that we have been thinking about. And just to give you the conversion factor, factors of like 10 to the 12 inverse megaparsec, they correspond to the frequency, which is like, 1 millihertz. And you notice that this value is interesting because this is precisely the frequency that Lisa, for example, would probe. And if you go to higher values of K mode, that would also mean that you have like the frequency also would increase. So you can also have some sensitivity, for example, from LIGO or its future versions or DeSiGo and so on. So that's basically the main idea. And now let me just end with this plot again.
What is the shape of the spectrum? Is it just...
Yeah, so I erased this part, but it's basically good. So it basically comes, so the tilt in this guy was 2m squared over 3 Hubble squared. So it's literally just the square of that. So you have pretty gradual frequency dependence. So that's pretty different from like what you expect based on like phase transitions and other scenarios. Okay, so now if you go back to this plot, then you would notice that you can put in new numbers here. So like 10 to the 11, 10 to the 14. And then you would notice that because of by this method, you can have extra parts of the primordial density perturbation parameter space where future experiments like Lisa or DeSiGo that they would be able to cover. Roughly speaking, these values, they're of the order of like 10 to the minus 6 or so. But what is interesting is that these are constraints or probes for a range of k that we otherwise do not have any idea about. Like we do not know what happens to the primordial density perturbations for those k's. But the point is, you would have sensitivity from these gravitational wave detectors.
Right? So I mean, it's true that we don't know what the primordial power spectrum looks like there, but we do know what the power spectrum looks like there today. Is that sufficient short scale just to assess?
But they're completely swamped by nonlinear effects.
Right. But doesn't that mean? I mean, so are you thinking of this as some kind of irreducible background for whatever Lisa would see from?
Yeah, it won't be background because they're still weak in the sense that like we are not thinking about like order 1 values of delta rho over rho. Okay. But the point is like everything is so nonlinear here that we won't be able to trace back to the primordial physics for these cases because these are very, very small.
I don't understand that. I have exactly the same question as Kleban, because I mean there is a lot of power today here. Wouldn't can you say it again? How come you can see this tiny teeny things if we have so much structure today creating waves, or your waves are still stronger?
Yeah. So the point is these things, these gravitational waves, they are generated when everything was very, very linear, when the modes just entered the horizon.
The question is things like supermassive black holes orbiting each other.
Yeah.
Isn't there background from that kind of thing?
For gravitational waves?
Yeah, exactly.
Oh, okay, sorry, I
Even for
misunderstood.
gravitational waves.
So I am not killed by the inevitable background.
Yeah, good. So this connects back to what Lisa was asking. Like, so there's a frequency dependence that you can predict for this setup. It depends on the mass of the scalar, and you also have some frequency dependence for example, the binary black hole contributions. So that would be the main handles.
But if it's much smaller, you still wouldn't be able to figure it out, is what you say.
If it is much smaller, then it's going to be hard.
Do you have any idea what those scales are like?
But at for these values, like for DeSiGo or also for Lisa, like the backgrounds, they're not
Oh, yeah,
They're
okay,
not
so you're
going to
saying
be
those are real things and they are not expected to be overwhelmed by whatever signal there is, by the existing
No, they
known
will see the
signal.
background.
I'm not sure that's true though.
But it depends on the
This
precise
record
value.
doesn't exist anymore, by the way.
Sorry?
This record, which was the really sensitive one.
Okay, so we have to rely on this one then. Yeah, but yeah, I think you can still do. It depends on again like what is the precise values of density perturbations you get. If you're at the borderline sensitive, then it's going to be difficult, of course, because you have competing backgrounds. Yeah.
I mean, the other comment he said is just you have to have an integrated signal over a long time, so.
That's going to be important for if you want to distinguish between different frequencies.
If you want to measure it at all. It turns out their signal to noise is like, it's very deceptive the way they present it. It's like, it's not a momentary signal, it's really the signal you get after they integrate over the whole time period. So you have to be really careful about that.
Okay. But,
So
yeah.
you're gonna say one more thing.
No, I'm done.
And then then we're just gonna thank you. Does anybody have any more questions?
Yeah.
Yes.
Can you comment if sigma is long lived enough that you actually don't satisfy the inequality, that it comes to dominate the energy density? How does that affect the signal?
Yeah, so what's going to happen is that you have these factors of f sigma squared. So they are basically over here. So if you're increasing f sigma, then the scale also increases. It actually ends up increasing the strength of the calculations. So the only reason we didn't focus on that, like you'd basically have a period of like intermediate matter domination, and like some of the technical aspects are a bit trickier, like when you want to compute gravitational waves. But cosmologically, like physically, nothing goes wrong with that. So, yeah.
Who tells you that there is no kinetic mixing between sigma and z? Is there some reason, some equation that I'm missing? Then you would have a correlation also.
Yeah, that's true. You could have that. Yeah, I'm just here assuming that there is no kinetic mixing to begin with between these two fields. But that's also like that would be interesting in the sense that you can have an interference effect, which is typically larger.
So I have a question.
Yeah.
You didn't consider non-Gaussianities at all.
We did not. Yeah, that's also interesting. So we typically would expect that if you have these quantum mechanical fluctuations from the bottom of the well, they would be non-Gaussian. Yeah. So that's for sure interesting.
That's like we worked on this scenario.
Oh, okay. So I'll take a look. Yeah.
Thanks, Soubhik, again.
Thank you.
People can continue to ask questions, but I'm going to turn off the recording. So now you can really let loose.